So my name is Anthony Skopatz, and I'm the communications co-chair this year. And I'm happy to announce that this is the largest SciPy ever, at about 450 attendees, a little in that neighborhood. So before we get started, I've got a few announcements here that I'm going to read off that affect the rest of the day. We'll do this every day. So the first one is that there's a reception tonight in the ballroom pre-function area at 7 p.m. There are lightning talk sign-ups downstairs on a big board, sort of right across the foyer from registration. You can find that there. There will be the afternoon coffee break today will be at 3:15, not 3 o'clock like it says on the schedule. So that's super important. Another schedule update is that the BOF You Win or You SciPy will now be moved to today at 1:30, whereas that takes the place of the Num Focus BOF, which has been instead moved to Wednesday, tomorrow at 3:30. Additionally, Wes McKinney will be doing a book signing today during the coffee break, right out there, right in front of the grand ballroom. So attend that while you're getting some coffee. And then finally, it is my pleasure to introduce one of the conference co-chairs, Andy Terrell. So.
Hello, everybody. Welcome to SciPy 2014, and I'm here just to go through a little bit about what the conference is this year, what some things we've changed, and thank our sponsors and things before we get to the keynote address. This year we had two themes, geospatial computing, and there's a lot of really exciting geospatial work happening in the Python ecosystem. And so here you have like the best and brightest in that ecosystem come together to talk about a lot of geospatial ideas. So if you ever want to learn how to interact with maps, interact with tools that Python can interact with GIS or other mapping tools or gridding tools, this is the place to find people. And you will find some of the leading experts. In fact, I have one looking at me right now. So, and then our second one is education in scientific computing. I think I was in the car driving one day, and the LA mayor said, education is the civil rights issue of our day. And so I was like, we have to do education stuff, because all my friends here go and talk about how we need to educate better, how we need to bring out our scientific computing aspects into the classroom. And there's a lot of people who've been thinking very hard about that and thinking very much about how do we teach our next generation. And so you'll get a lot of education about education here, and so it's something that I hope everybody can take back to their classrooms and their day jobs and things like that, and help provide more scientific computing knowledge. Next, I just want to show a map of like who's here. If you looked at this map several years ago, you would have seen pretty much only the U.S. and pretty much nothing anywhere else. The U.S. is still very centric here, but we do have a global reach. And while we do have 450 participants this year, we also have all 6 inhabited continents. And thank you, South Africa. We appreciate the two of you. And so I think that you will find as we continue to grow and diversify, we really want to make this conference not just about the U.S. audience, but much more broad about how do we make scientific computing around the world a goal that people can all come here and share with and contribute to. Finally, I have 3 sections: what's new, who to thank, and who to blame. This year we changed Birds of a Feather quite a bit. In the past, Birds of a Feather were like, here's an open room and here's a sign up, and there wasn't much organization. What we found was that people were lacking that need to communicate about critical issues in libraries. For example, which color map to pick in Matplotlib. I think that's going to happen in a BOF. So we went out and found the most controversial people and the most controversial topics and tried to get them together so people can go talk to them. So I expect the Birds of a Feather to be very entertaining kind of aside for people to see between talks. There's also, so you already saw the swap, and there's some extra slots that might get filled up in the schedule, but we don't know yet. But we do have Thursday afternoon 3 slots if there's somebody who wants to organize an impromptu panel, come talk to me. Since we lost the idea that you could just sign up and talk in a room, we introduced open spaces this year. So there's rooms available for impromptu meetings. And if you go down to the same place where the lightning talks are, there's rooms there that you can just sign up and say, we're going to hack on, for example, OpenSL support in Conda or something. So you can kind of go and actually find places to actually meet and do things. And so they are basically what BOFs were last year, but you still have that impromptu meeting. Feel free. We have the center until, I believe, midnight every night and things like that. So you can work here and you can do a lot of stuff here. We also have a lot of social events, and last year there was a lot of complaints that our BOFs were the same times as the social events, so now you have to pick to not go to the social events. Another aspect is we added 3 days of lightning talks. Every year, lightning talks are the most fun kind of part of the conference, and we wanted to make sure everybody had more time to actually participate. So there are 3 days. We are asking, since they are so popular, that you only sign up for one, for an individual, and for organizations, we ask you to limit it to 2. Now, if we get to Thursday and there's nobody signing up, we can bend those rules, but just to make sure it's a fair place for everybody. And finally, we added a job fair this year after many requests last year to talk about issues around how do we employ ourselves and how do we keep our graduate students in the community and things like that. And we reached out to a lot of our sponsors who hire the best and brightest from this conference, and they're right outside. There is an official job fair at the reception tonight, but some people are starting to set up their tables and they'll be around whatever. But if you plan on meeting any of the job fair, be sure to be here at 7 p.m. tonight, and that's when everyone's going to be there. Okay. So next, on to who to thank. InThought is our institutional sponsor. They've been here supporting this conference for the last 13 years. They do a tremendous job coming and making sure that everything gets done, making sure all the T's are crossed and there's funding available and the risk is taken for making sure the places are put together. I mean, people don't know this, but this conference was probably started planning 4 years ago when Leah signed a contract that we're going to get cheaper hotel rooms and that sort of thing. So InThought is a leader in scientific computing. They're definitely the people who make this a community conference. And if you see anybody in these nice blue shirts with Continuum on it, please thank them. They're a huge benefit to our community. Our second big sponsor this year is National Institute of Standards and Technology. If you're from the National Institute, if you could stand up. I know there's many of you here. Okay, I don't see. There we go. So this is Dave and some others. So NIST is huge. They are our platinum sponsor this year. They did a huge amount of work to give us money to make sure that we could have this happen. And if anybody has ever worked in the government, you know how hard it is to push out funding in these days. And I really thank these guys for their Herculean effort. And the final sponsor I'll mention today is Real Massive. Sorry I didn't get your name here. If there's any Real Massive folks, can you stand up? I know I saw 3 of you earlier. There we go, the great shirts. My understanding is they're hiring and they're doing great stuff. So definitely go find these guys. The best part is they're here in Austin, so you get to live in a cool city. And who to blame? Oh, it chopped off the top there, but this is a screenshot of the program committee. If you're part of the program committee or the conference committee, if you could stand up, please, and we can give everybody a round of applause. So, if there's any issues that arise, there's several of our phone numbers are on the website. I'm not going to tell you where exactly they are, so you have to at least Google that. But please reach out to any problems, any complaints, any praises, anything you need. This conference committee has been working for a year to get everything off the ground, and I think that they've done a tremendous job, and I really have appreciated working with this team. So, with that, I'd like to introduce Lorena Barba. If you'd like to come on. So Lorena, I got to know Lorena about 5 years ago, and she's it's probably one of the biggest pleasures of my academic career is knowing Lorena and seeing all the great work she was doing. Back in the day when GPU computing was hot, she was a leader in the field, showing she was the leader of the field. She's very much the leader of the field today as well. Sorry, Lorena. And she also speaks a lot better than I do, so it's a nice thing. She's currently an assistant professor at the George Washington University and Mechanical and Aerospace Engineering School. She just won the NSF Early Career Award. I guess it's not just anymore. Time flies, but 2012, and CUDA. She's a CUDA Fellow by the NVIDIA Corporation, Amelia Earhart Fellow from the Zonta Foundation. She is an avid Twitter user, and this is the best way to catch her and talk at midnight. So definitely recommend following her. And one piece of work that I think is everybody here should probably go read from her is this reproducibility PI manifesto, and I think that she's become well recognized as a leader in carrying the field of reproducibility and to the scientific field. And without no further ado, I'll let Lorena give us her talk on computational thinking and computational learning.
Well, thank you ever so much, Andy, for that introduction. Let me set myself up here. Let's see, it was 3 cables that I needed to set up, right? This is on the edge of feedback. And I accidentally added a slide. Okay. Well, thank you ever so much. Thank you, Katie, for thinking about me and suggesting my name, and thank you, all of you, for this opportunity to be with you. Actually, I haven't been to SciPy before, so it's an introduction for me as well to be with this community, and I'm really, really happy for this. I'll thank the sponsors that have supported my work in the past few years, first of all. And I'm going to do something that is not customary in an academic world. And that is, I am going to dedicate this talk to my grandparents. On Monday morning, as I was packing my bags to come over here, I heard that my nonna has left, and I was very, very affected because she was a very important figure in my life. She left only 4 months after my granddad, who left in February. And because they were a very important figure in my life, and because they were very proud of me, I want to dedicate this talk to them. This was the end of a 75-year love story and an inspiration for me. So let me tell you a little bit about me, because as I said, I haven't been participating in this conference before, so you may not know. I come from Chile, that little sliver of a country down there, and I studied mechanical engineering at first, so perhaps an unlikely background, except for a few over here. Many of you are computer scientists or applied mathematicians or physicists. I'm an engineer, so I'll tell you a little bit about engineering history even a little later. This is my campus. Andy actually visited. As you can see, a beautiful campus in front of the sea. I used to watch the Pacific Ocean every single day in the morning as I came to the university. But as you can see, there's a big flight of stairs to get up there, so it's quite tough when you're late for an exam. It's 109 steps to get up there, and I counted them. I did my PhD in Caltech. This is my favorite image of what Caltech is. The pranks, the famous prank of the Hollywood sign, indicated how self-absorbed and egotistical and grandiose people think they are there, including me, I guess, a little bit sometimes. And that's why I'm telling you so much about myself. So just a couple more things. You can read about the things I do on my website, and I blog sometimes, not very often, about things I care, but you can find out about some of the research that we do in my group. Computational fluid dynamics mainly, but we have veered towards biophysics, GPU computing, and some applied math, sometimes on the edge of between applied math, algorithms. We talk to computer scientists and high-performance computing. So this gray area that is very hard to identify, and we call it scientific computing. One of the recent applications that gathered a lot of attention was our work on flying snakes. So just to give you a flavor of some of the things that my students and I are working on, we use computational fluid dynamics to study the physics of flying snakes. So we have a paper out, came out in early this year, March, I think, a collaboration with a biomechanist and experimental fluid mechanician as well. We have another project that I'm very excited about, which actually uses Python in the application of biophysics. And this is one example of the way that we do work, which is that we try to use the leading edge technology and in an open fashion. All of the codes that we develop in my group are always open, and they are deposited in an open repository at the moment of submission of a paper. And we also are publishing all of the data that appears in a paper, the figures in the plotting scripts for any of the main figures that are in a publication. We deposit a lot of our objects, the objects beyond publications, on the repository Figshare. This is one of the papers that just came out a few months ago using this code, a code that uses Python and GPUs for an application in biophysics where people are not so accustomed to high-performance computing. So our experience was when we tried to, do a parallel code that used multi-GPUs and was, 500 GPUs. That was the first paper we published. People didn't pay that much attention in the application world because biologists don't really want to be logging into supercomputings or applying for allocations or all that stuff. So we moved to something that was more accessible, and Python was the ideal language to do that. But of course, we had to as well apply performance, and that's where the GPUs came in. We are taking this work now to another application which I'm excited about, which is computer modeling for biosensors. The idea is to use the electrostatics approach to study antibody-based biosensors. These are used for detecting a lot of different pathogens, bacteria, and so on. And this is an application that you can imagine is vital for public health, environmental analysis, and of course security. But it has other applications in pharmaceutical industry and food as well. So we think that through collaboration, again, cross-disciplinary collaboration between computational scientists and an application that hasn't been impacted greatly by modeling, this field is basically experimental so far, I think we can make an impact. So if you, going back to the paper, this previous publication, for example, one of the things that I'm proud about this paper is that we did a very, very thorough convergence analysis, a very serious study of the accuracy, the errors of the model and the code, which is not really something that this community is very accustomed to. So we bring from our CFD tradition some of the tools that we know, and we want to produce some impact through this cross-disciplinary collaboration. But I think the reason I'm here, and I'm very excited that SciPy has decided to have a specialized track on education, because it's a very exciting time to pay attention and to be involved in education. This has been building up for a few years with some reports coming out of the President's advisors teams, and there's a PCAS report of 2008 and so on, expressing concern about the education of our, especially science and technology undergraduates. So there's a lot of interest in this topic. So let me tell you a little bit about what I've been doing in this field. So first of all, my first academic position was in the University of Bristol in the UK, and there what I started to do was record my lectures. I was lecturing the usual style, and I was writing on a whiteboard, and I was using different types of devices to capture that, just to share with my students so that they could revisit, because I was aware that students, they space out. I space out if I'm sitting in the audience for too long. So I thought, well, I'll record the lectures, put them on some site, and they can review it afterwards. The students liked this, but I had to progress further. So from 2009 to 2012, I recorded my lectures in this form with different technologies that I can tell you about more if you're interested in the break. And I started depositing those recordings on the Boston University iTunes U channel. Now, this funny effort, one-woman show with recording my lectures and processing them on QuickTime and putting them on iTunes U, started dominating the iTunes U channel of the university. It became, as you can, this is a screenshot from February 2012, where you see that 9 of the top downloads are the stuff that I was sharing. So, in that sense, gave me an indication that, this is not yet catching on, but it was being used. So then, while doing some preparatory research for preparing my NSF proposal, I was looking for techniques to increase the amount of interactivity in the classroom, and I came into this idea of the flipped classroom. After reading about it, I decided that it was just what I needed and just what I was looking for, and I submitted my NSF career proposal in July 2011. And you can see that this idea took off really, really dramatically after that. So I sort of identified something just at the right time. Now everybody's talking about the flipped classroom, and is something that I have some experience in, and I've been also writing about how I do this. So in very simple terms, what the flipped classroom is the simple idea of moving what is most difficult in the learning experience, which is assimilating knowledge and internalizing knowledge and solving problems, to the classroom time where you can be supported by your peers and your instructor. And to be able to do that, you have to displace that easy part, really, which is simply being exposed to the content for the first time outside of the classroom. So a lot of people equate this with watching a video of the lecture. And that's natural, because the technology today makes it very easy to record videos and share videos. But it's not the key to have video. You can use a flipped classroom approach with readings or any material. And in fact, often when you talk about flipped classroom, people from the humanities world come and say, well, this is nothing new. We've been doing this for a long time. Because, yes, of course, if you're teaching a literature class, you have to do the reading and come prepared to discuss in class. Well, yes, they've been doing this, like, flipped classroom that we call it today in other fields. I think what's different today is 3 things. First, that this is catching on in science and technology fields, in engineering. This is unusual in engineering. Second, the ubiquity of mobile devices and the ease of recording videos and sharing multimedia, I think is an enabling technology. It makes things different. And third, the new research about how people learn that supports with evidence the decision to remove lectures from the classroom and use active learning. There's now a substantial body of research that supports this idea. So it's a little bit different in that sense. So in 2012, I taught a computational fluid dynamics class, and I had previously, I told you, had been recording my lectures, straight-on lectures that I was doing at the time. And, I got the NSF Career Award, so I had to now do this. And I flipped the classroom in my CFD class in 2012 using these previously recorded videos that I had already done. But I put them on YouTube this time. I cut them into smaller pieces and put them on YouTube. And over time, I checked only Sunday, these videos have been gathering views. They're just there. I've never done any dissemination except for, recently maybe I'll tweet about it, when I go in and notice that they have so many views. They have gathered almost, 237,000 collective views if I add for all the 30 videos or so, just sitting there for 2 years. And so it's exciting to think that people all over the world might be using this. I get some emails sometimes of appreciation from students who actually find this material useful. In addition to this, I've been starting to use other tools. One of them is TED-Ed, where one video can be embedded in a short quiz with some context materials, and make a little lesson, online lesson out of your video. This is a neat little tool, but you might not know that it's actually, there's evidence to support the idea that what the psychologists call retrieval practice helps to embed the learning. So the simple fact of having a little quiz that makes you just say back what you just heard, or answer a very easy, even multiple choice question, helps retention. So I wrote about, I've been giving some talks about the flipped classroom, and I've been invited to do some webinars and so on, and there's a couple of recordings of talks I've given about this topic, and I have written something up as well that if you're interested you can read on my website. And then I started doing some other things. I decided, well, I was using this discussion site called Piazza, and I thought, well, why not just invite anybody who wants to listen and join into our conversations with my classroom, log into Piazza. So I posted somewhere and invited people to join in, and about 100 or 150 people, students from who knows what country, joined in and participated in some of these discussions, and this was picked up by the company, and they thought this was very interesting, and they wrote a blog post about it. So these are some of the keywords and about this effort. Flipped classroom, screencasting is the method to record the videos. I don't know if there's a mic around for question, but I wanted to pause at this point and ask if anybody has a question about this. Is there a mic for questions, or should I wait until the end?
Just repeat the question.
If there's any question at this point about the flipped classroom or anything, I'd be happy to answer. Yes?
I'm wondering, is the classroom vacant to the high school level, or is it mostly at the college level?
I would say that it's more prevalent in the high school or the school level in general than higher education. So if you read about this, there's some questions still about, well, is anybody trying flipped classroom in higher education? I read the other day in some question in Stack Exchange, and it's less common. In school, they've long been moving, especially elementary school, of course, long been moving to active learning, and this has been slowly going up the levels of schooling, I think. Yes?
I was curious about intellectual property rights. Sometimes universities can be an impediment to sharing code. If you've run into anything about
Right. So for code, my policy is I write it in my proposals. Each and every proposal will have a commitment that I will share openly the code. So once that proposal is accepted, the university will normally accept the award, and then the proposal becomes part of the contract, and I have made a commitment to do this, and so it's a non-issue. Yes. But you have to plan ahead for that.
What about things like your videos and other instructional materials?
All right. So this question, I repeat, is about intellectual property. The previous one about code, and this one about the instructional materials. Some universities may not have this this employment contract, but the AAUP recommendation is for universities to actually grant copyright to the faculty on their instructional materials. And so if your university is compliant with AAUP guidelines, they would award you the copyright. Some of the logic here is that if you move to another university, you should be allowed to teach the same class that you previously developed, for example. And books, textbooks, and so on are the intellectual property of the faculty often. So my policy is that to share everything in a Creative Commons attribution license. That's simply what's consistent with my open policy. And I would say normally I just go for the ask forgiveness and not permission. You know? Okay. So let me tell you a little bit about how I use IPython notebooks. So teaching using IPython notebooks was the topic of a tutorial yesterday. I was an all-afternoon tutorial, and it was very exciting. And I think that IPython notebooks are really a killer app for teaching computing in science and engineering, and I'm going to tell you why. But let me start by sharing some of my experiences. So I told you about my CFD class. I put the videos on YouTube. I flipped the classroom, and then last year I was invited to do a summer school in Argentina to teach some CFD, and I decided to create some IPython notebooks with this material. I had been using this particular exercise, which is called the 12 Steps to Navier-Stokes, and of course a tongue-in-cheek allusion to the behavioral recovery programs. We first had used this set of exercises as sort of a boot camp for my students coming in my research group, and they just did it on their own. And it was simply a set of written out equations on some pieces of paper. And I used this as an exercise in my CFD class when I started teaching the CFD class at BU. But last year, we first created a set of IPython notebooks based on this classroom exercise, and I used it live in this summer school. What was interesting was the way I used this was, it was a two-day event, 8 hours each day, and I had about 20 students, and these were all pre-prepared, and I had the students go through these lessons at their own pace, and I would go desk to desk, helping and asking questions. So some of the students, by the end of the 2 days, completed this assignment, which consists of 12 steps, to the point of coding your own two-dimensional Navier-Stokes solver. A cavity flow is a classic problem in CFD. This was already rather impressive to people that have mentioned it when I did it in my class, where my students took about 5 weeks to complete this, and like to say, wow, 5 weeks to do your own, to code from scratch, a 2D Navier-Stokes solver, that was already rather a good thing. In this case, of the 20 students, about 4 of them completed this assignment in 2 days, 2 intense days at the summer school. About 8 of them in the middle, right, reached maybe 8 of the lessons, which takes you up to 2D Burger's equation. And there was, 4 in the bottom tail that got to 4 or 5, lessons 4 or 5, which is kind of normal, what you see in a classroom distribution. But already for those who completed the module, they had achieved in 2 days what the students in my classroom took 5 weeks to complete, which I thought was pretty amazing. It depended on their previous programming experience, of course. So, this past spring, 2014, I was tasked to teach a classical aerodynamics course. This is normally a theory course, so the standard way to teach this course is you actually write, theory on the board. Students write the theory on their notebooks. There's a good anecdote from, I think, Eric Mazur here, where he says that the lecture method is this method by which the notes of the professor go to from the notes of the professor, the content goes to the notes of the student without passing through the brain of either. Right? So having experienced before the flipped classroom on my CFD class, I didn't want to use the lecture format, obviously, but also didn't have the time or the materials at hand to record videos. And so how do I do this, I thought? How do I leave class time for this problem solving and assimilation of knowledge? And how do I create materials for the students that they can be prepared for class? So the experience the previous summer with these CFD Python notebooks in Argentina made me think that this was the solution. But what should I cover? So I thought to myself, what is the one thing that I want aerodynamics students to know for potential classical aerodynamics? The answer was panel method solutions for the analysis of lifting bodies. And so I thought, okay, this is the one thing I want them to know. I'm going to build a set of lessons on IPython notebooks to bring the students step by step from the most simple potential flow solution to the point that they can do 2D lifting body panel methods. So with the help of my very bright and dedicated PhD student Olivier Mesnard from France, we set out to develop these lessons that would take the students in this provide a scaffolding for the students to follow. The students were guided to read through the notebooks, work out on paper any mathematical derivations that they needed to, write their own version of the code, and usually typing in an open, fresh IPython notebook or maybe a Canopy console. And in class, I just walked from desk to desk asking questions and challenging the students to explain why they were doing something a certain way, or to test different parameters, or explain to me what size is that array. Do you understand? Is that a tall and thin array, or is it a flat, long array? Do you know what that function is doing? What's the end or the beginning of linspace? And so on. And asking questions to force them to think about what they're doing, because otherwise they'll just copy-paste, right? And so this was the mechanics in class, and then they had time to read the material on their own afterwards. So one day, a student was working on lesson 6, which is called Lift on a Cylinder. He was experimenting, as I had instructed, with different values of the relevant parameters. The classical solution of flow around a cylinder is obtained by a fundamental solution we call a doublet, plus a uniform flow, plus a vortex, a point vortex in the middle. And if you add this point vortex, you get a flow that is no longer symmetric, and you get lift. So the student started experimenting with the value of this vortex, the parameter, and he got that solution that is at the top, and he raised his hand and said, "Professor, the stagnation points are gone." And I went around and said, "What do you mean the stagnation points are gone? Normally you would have 2 stagnation points on the lower side of the cylinder. Look, they're not there anymore." "Oh," I said, "well, what value did you try for the circulation?" He said 10. "Well, okay, try 5, or try 4. I don't remember exactly what numbers they were. I chose a couple of numbers to show you a picture, as I was preparing this talk. But at some point, he got just the right answer, that he thought, oh, the stagnation points move out of the body. Now think about how normally a student would be exposed to this. I'd write the 3 solutions on the board, on chalkboard, and I said, here's the 2 stagnation points. As I increase the circulation point, the stagnation points moved away from the body, and I have 3 pictures on the board. The students write the 3 pictures on their notebooks, and that's it. Probably they'll never remember it again, right? I am sure that this student experienced at that point something that he will remember. And this gave me sort of a pause for thought about what was happening in the classroom, how the students were experiencing this. Now, let me now take a historical sidetrack to understand the consequence of this anecdote from the perspective of engineering. I'm an engineer professor. So we're going to take a little detour into history and sort of understand how engineering colleges came to this situation where they're criticized for a curriculum that lacks in industrial relevance and students lacking problem-solving skills. So the situation that led to this was a very serious revamping of engineering education that happened after the Second World War II, the Second World War. So this is explained in this very nice paper, a very highly researched and fascinating paper about engineering education. In this, the author walks us through the changes that happened in American education from the 19th century onwards. In the 19th century, the engineering schools emphasized practical skills. Faculty were expected to have industrial experience. They were not expected to do research. And even though as shop culture moved on to school culture, there was a lot of hands-on. There was a hands-on approach to teaching, and the schools were interested in making good practical engineers. The faculty weighed more heavily how than why. After 1920, some European professors, European-born and educated engineers came to America. People like Stephen Timoshenko. We still read his materials books, and Theodore von Karman, the aerodynamicist, and they brought a different view. They planted the seed of this transformation in engineering education, whereby science, theoretical content started to increase in importance. One particular person that was involved in this was Theodore von Karman. He had a tremendous influence in a whole generation of aeronautical engineers by introducing the work of Ludwig Prandtl on fluid dynamics. And these European engineers were really accomplished mathematicians. Their approach became widely accepted after World War II because there was a sharp increase in federal funding at the time. And this large influx of money displaced the previously industry-funded research, and the engineering deans learned the equation. Schools started seeking to hire faculty that could attract research grants and emphasize engineering science, and there was this big gulf created between the faculty interests and the students' interest. This is how we got there. And so engineering education was completely transformed after 1945, and many since then have been commenting on this unbalance caused by focusing too much on theory. Many reformers since the 1990s have been suggesting a greater emphasis on design, for example, and to try to reverse this unbalance. But by and large, teaching methods have changed very little since the mid-20th century. Students sit and get knowledge that is passed on by the students reciting facts, and then they're examined in those facts. It hasn't changed very much. Now it's more crowded. Now you have devices in addition. Why is this a problem? Well, it's a problem because of the nature of knowledge itself. The traditional view of knowledge is that you might associate it with facts or propositions, and then learning becomes remembering. This focus is a very limited and utilitarian focus, the focus on propositional knowledge. In reality, remembering is not that useful. I mean, think about how you work, right? Do you remember anything? Could you code without Google? Could you do your job without? Does it even matter that you can't remember things? Remembering is really not that useful, and memory is contextualized with your culture. Some Aboriginal cultures might remember very deeply into their past ancestors because that's what they needed to maybe negotiate with the clan next door. But that is completely cultural. So remembering is not how knowledge works. Knowledge is distributed. Our modern view of knowledge is much richer than just facts and propositions. We say that knowledge is distributed, and this is why it's okay that you have to Google everything before if you're a coder. So today we speak about connective knowledge, a knowledge that is created, shared by an interconnected community of individuals. This is the modern view of knowledge. So in this view, learners need to participate and engage. This is their role. And this is why open education is so important, and it serves a pedagogical value. Open education involves sharing, not just access to material, because if you think about open educational resources, people put things out there, but it does create access, which is a good thing, but there's very little reuse, very little connections between things. And so it's more than just putting things out there. It's creating an interconnected community. That's why this is so important. That's in the same way that open source software works. So there's a Canadian researcher called Stephen Downes that proposes this statement: science is a conversation. Stephen Downes has a long history of commenting on education technology, and he's a philosopher. Science is a conversation between scientists and their body of knowledge, a conversation between scientists, and think about it. This is how we work. You're constantly having conversations, and this is how you create knowledge. You couldn't do anything without those connections. Forming connections between concepts, ideas, artifacts, phenomena, people, and that's how you create things. This is how knowledge works. So, last year, SciPy had a specialized track on reproducibility. This year there was a tutorial as well. Why are we concerned about reproducibility in the context of computation? Why are we concerned about that? Because computer simulations, in fact, create scientific knowledge. This is the reason we're concerned about reproducibility. We want to know when we have evidence that claims to scientific knowledge that come from simulations are justified. It's a deeply philosophical question. How do we show evidence that simulation gives a reliable result, that a claim to science that we're making is acceptable? So in this crowd, I can't use an audience response system. It's a large crowd, and the setting doesn't allow it. But I asked this question in the audience, a small audience in the Science Uncertainty Quantification Conference a few months ago, and most people agreed that indeed science does create scientific knowledge. I would have a show of hand here. How many people do agree here that simulations create scientific knowledge? So we do agree, mostly. So computing creates knowledge. In that sense, it's a form of learning. This is my main thesis today. If computer simulations, computing, creates new knowledge, then we agree that it does, then computing is a form of learning. Now, computing interactively, from this point of view, is a conversation with the system under study. Now remember the previous statement about knowledge, that knowledge is created by conversation and interaction. So computing interactively then is a very important method to create knowledge, and computational scientists are literate in this type of conversations. This is what we do. We are used to hearing about skills and capacities, but it's more appropriate to talk about literacy, I think. And others think I'm, of course, connecting other knowledge. Nothing that I say is completely original, I'm just connecting things, right? And in fact, there's a theory, I'm going a little bit deeper into philosophy that you might want, so try to keep up, hang in there. There's a theory of knowledge called connectivism, the idea that knowledge is distributed across a network of connections, and therefore learning is the ability to construct and traverse those networks. And you should be accustomed to this idea from the open source software community. So what I'm suggesting in general is in tune with this theory called connectivism. There's a neat little paper by Patrick Dillon, who is an emeritus professor at Exeter and the School of Education and Lifelong Learning. It's a tough read, but it's really neat if you hang in there, read it a couple of times. And it talks about cross-disciplinary work as a creative and integrative activity. Working across disciplines, he says, has the potential for creating something novel. We know this as computational scientists, that creating across disciplines, this is very attuned to what I feel from my research work. It's inherently creative, he says. But there are obstacles, of course. There are tensions. Language is an issue sometimes between disciplines. He explores the philosophical and methodology issues of this, of working across disciplines, and studies a couple of written works that are cross-disciplinary. And he suggests what he calls a pedagogy of connection, that there are teaching and learning strategies that can be deployed to actively promote creative work across and between disciplines. So his concern is working across disciplines, which he associates, like others do, to a highly creative work, a transformation, creating something new forms of knowledge. And he's offering this pedagogical framework for working across disciplines, because this work is integrative, and he says we require tools for working in this way. Integrating ideas from different disciplines requires crossing boundaries. So you need some objects, boundary objects, to cross these boundaries. And he says, well, you're used to think about some general traits for creativity like fluency and flexibility, but there are some, in addition to these, that he calls tools of connection. Tools of connection are comparison, association, analogy, mapping, tools that facilitate and engage learners in transitions in their way of thinking. In education, if you read the education literature, you'll find a lot of jargon. Some of the words that they use, for example, are interventions. People talk about interventions. And this is all over the educational literature. Interventions involve the use of tools, tools that facilitate connection, that engage learners in a transition. Stephen Downes, I mentioned before from Canada, he talks about personal learning, which is about the individual's growth, something that is, you can't really give knowledge, transfer knowledge. It's an individual experience. So here's why I think IPython notebooks are a killer app. So not only in computational science, but in many STEM topics. Computing interactively, I said, is having a conversation with the system under study. It's a way to create new knowledge. And these media-rich, interactive objects are tools of connection. So I'm tying it back to learning theory, and thank you for your patience, but this, I think, is the reason why I am so enthusiastic about this creation, about this object. They engage learners while they have a personal experience connecting ideas, artifacts, and things, methods, concepts. And so this is the main thesis of my talk, that computing is a tool for learning, human, not machine learning. We already agreed that computation creates new knowledge, and so we know this in the context of research. Now I'm moving it to the concept of teaching and learning, in the sense of some of the philosophers that I quoted, the computing is a tool of connection. And IPython notebooks are boundary objects that allow you to connect disciplinary content, like aerodynamics, to your experience. When my aerodynamics students discovered that the stagnation points in the cylinder, moved outside of the surface, he had an experience. He really learned this. It's a far cry from just transcribing the notes of the professor to his notebook, right? So, the phrase computational thinking was first used by an MIT professor, Seymour Papert, in 1996. But 10 years later, in 2006, it was popularized by Jeanette Wing on this short viewpoint in the communications of the ACM. Jeanette Wing was assistant director of the SciPy directorate in NSF, and she had some big influence on large investments in computational science research. This little paper had a lot of attention from people and many citations, as you can see from Google Scholar. She suggested that computational thinking is a fundamental skill for everyone, just like reading. And in her talk, she usually makes reference to computational biology, interacting with computation to make significant advances in genomics and so on. She often talks about machine learning as one particular method that had great influence in many fields. And in our daily lives, like in e-commerce, for example. So I want to move the conversation from computational thinking to computational learning. This is the thesis of this talk. So to wrap up, I told you this anecdote of using IPython notebooks in my aerodynamics class, and contrasted this to how an engineering student would traditionally encounter this material. And then I went on a bit of a historical sidetrack to explain why it is that we teach engineering with such detachment from the real world, such focus on theory, and noted that this idea of one-way transmission of knowledge really is not compatible with the nature of knowledge itself, because you can't give knowledge away. We cannot produce knowledge for somebody else. They have to experience it themselves. And this is why open educational resources like OpenCourseWare are not transformative by themselves. Open education should include the full share, reuse, remix capability, not just putting some materials out there. And in fact, it should include students sharing their work as well, because that's how they're going to connect with others. So this is the idea that knowledge is distributed, and it supports the pedagogical purpose of open sharing. Second, the reason we care about reproducibility in computational science is that computing creates knowledge in research. And this it supports the pedagogical purpose of computing, and using computing for scientific discovery is in the context of research. Using computing for learning in the context of education is my implication for our specialized track in this conference. So computing is a form of learning in in my example, aerodynamics, maybe in mathematics, in fluid mechanics, in any application I can see computing being used to explore that body of knowledge or that content. Embedded in the curriculum, this would be my ideal, computing embedded in the curriculum throughout everything we do. So this thinking is aligned with this modern connectivist theory of learning, and I took you a little bit deeper into philosophy that you probably wanted to, but to just give you some evidence, some foundation, looking into this idea of pedagogy of connections and working across disciplines, and this idea of boundary objects. People have been thinking about this very seriously, and the reason I bring this up is it makes me very excited about a tool like IPython notebooks for education. So the rhetoric about computational thinking, in the rhetoric about computational thinking, the point is often made that the key of this is using computational thinking in other disciplines. The suggestion is that working across disciplines with computation. So beyond computational thinking, I'm proposing computing as a learning tool. So this is the the title of the talk and what I end with. And I just want to leave you with a short announcement, and it is that we are going to apply this in the fall with some colleagues. That one of them is here in the room, David Kitcheson. Two other colleagues, we are going to work together, connect our courses that we're going to teach in 4 different campuses. I'm going to teach in numerical methods. We call it practical numerical methods with Python. I'm going to teach in GW, and David Kitcheson is going to teach at KAUST. Ian Hawke at Southampton University in the UK, and Carlos Jerez in the Catholic University of Chile. We're going to teach our courses in our local campuses, and we're going to collaborate in the creation of these materials. Everything will be IPython notebooks created collaboratively and openly on GitHub. And at the same time, we're going to attach a MOOC to this, so everything will be open and people will be invited to join us in this learning experience. We're not going to associate ourselves to any of the MOOC providers. We're going to do it ourselves. We're going to install our own instance of the OpenEdX platform on the cloud. I'm looking for cloud sponsors, in-kind sponsors, by the way, if anybody's in here from that field. And we have some support from a couple of sponsors, so completely independent effort, because MOOC providers have mostly ignored the social aspect of learning. So this is what we want to here exemplify. Use the way that we work in open source software for developing a connected course. So with that, I thank you very much for your attention.